Hi, everyone. Welcome to another Common Lisp study group. Um, I'm Ram Vedam with Atlanta Functional Programming, for those of you who are just joining in today. We are continuing our discussions of cl-transducers, a library I mentioned and introduced last week that is dealing with composable algorithmic transformations, as the library author would like to call it. For those of you who missed last week's presentation, a quick 10,000 foot overview of it. cl-transducers is nothing more than a library that allows you to essentially leverage the transducer concept that was introduced by Rich Hickey in Clojure. It does overload the transducer concept for those of you coming in and knowing libraries like series, where transducers meant you take in a series and you return a series inside of a transformation. So it was more like a linear transformation between one collection and another collection. But transducers in Clojure is slightly different in that they are, number one, functional in that it they try to be as immutable as possible. You're always creating new collections in between each of the individual transformations. Additionally, the composition approach that they leverage follows the Clojure-like composition of approach of taking a series of lambdas and returning a single lambda object that is uncallable that can then pass into the transducer API to actually do reduction. Um, I showed a lot of different examples last week, but I'm going to focus my efforts today mainly on two main things that I kind of missed and I want to kind of experiment with today, and that is the fset library extensions that they provided for transducers, as well as I read in their documentation as well about some series uh, extensions, but I don't know to what maturity um, those series extensions are. Uh, as usual, before I really dive in, couple announcements. One, Atlanta Functional Programming is looking for speakers. We do hybrid online and in-person meetups. For those of you who are interested in giving a talk and are not in the Atlanta area, feel free to reach out to me or Judd. I tend to squat on Slack in Tech 404 as well as functional programming has Bugram. Feel free to reach out to me there to actually give your talk topics and then I'll get them scheduled. Additionally, if you're on the Lisp Discord server, I'm Bugram on the Lisp Discord server too. So go ahead and reach out to that. Also, in terms of Common Lisp study group topics and stuff, I am looking for additional topics for folks who would like me to discuss, either libraries and or what's it books suggestions. I am going to start in the next couple of weeks. Paradigms of Artificial Intelligence Programming, which is a book that I've been wanting to cover on our study group for quite some time. I just haven't had a chance to really sit down and try to figure out what would be the best way to actually do that. So hopefully within the next couple of weeks, if you are on the meetup page, I will do some more formal announcements regarding that. So that way you guys can stay up to date. And if you need to purchase the book and or find the ebook copy, I think there is an ebook copy by Peter Norvig because the publisher gave him the rights to actually um, release it out somewhere. You can grab an ebook copy there, or go to your, find book dealers to actually grab a copy, which I do encourage people to still buy because it's still a very relevant book, even in today's day and age, with most people attempting just mainly ML based uh, AI algorithms rather than some of the more classic algorithms that that book covers, as well as other books in that area. Um, So last time when we talked about transducers, we kind of went and finished with this one example that I introduced related to just grabbing something from a cons value and creating a cons. You may have noticed the uncons and cons are actually still, well, uncons more than cons is prefixed with the transducers package, and that's because of the fact that uncons in normal common Lisp kind of relates to either car and could, depending upon what you end up doing, and then you'll end up uh, writing kind of a recursive algorithm to actually attach to that. But if you want sort of a transformation pipeline to be able to like uh, unwrap a value from a cons and then use it inside of a function, we have to do something along these lines. So this way, the um, uh, algorithm doesn't get cluttered with boilerplate related stuff for unconsing and grabbing the actual value from the collection and being able to pass it into the pipeline. So this approach ends up resulting in more of a uh, declarative style of computing a value for a given computation. Additionally, for those of you who may be curious about, and this is something I didn't cover last week that I was curious about myself, that is why is cons is actually prefixed with transducers. So if we end up just using normal cons here instead of transducers cons, what happens? Um, when we run this, you'll see that you end up getting an exception here, and the exception is what's actually being passed into the composition function, not from the cons itself. So cons might end up getting some information, but it actually is technically invalid. And the reason for this is in transducers, they had to do some additional work, from my understanding, to actually get these kinds of common Lisp standard or API functions to work with the paradigm that was trying to be encouraged by the transducers package. So if we end up doing this, you can see here that we'll end up getting what we had last time, which is the unconsing being able to pass in, but the reduction was it's also constructing us a proper list, well, a property list here in this case. So, like I mentioned, there are two additional packages, I guess you could say, or extensions to transducers, mainly dealing with immutable collections. One is the quite um, recognizable now fset library that contains immutable collections that are for uh, pure functional based programming. So to put this into perspective, most of you who have been following us on the study group and have been doing Common Lisp in their free time, just to review, most of the common Lisp data structures are technically modifiable through the generalizable set f expander. Uh, that means that although you have functional APIs in the sense of map car, map can, all the map functions, reduction, concatenate, and so forth, you also had the destructive operations nconc and their ilk also available to you for the same set of data structures, and the reason for that is because of this modifiability. So what FSET set out to do, for folks who haven't actually watched my series on FSET, it actually decided to recreate a lot of the common Lisp APIs for the purposes of actual use in I guess you could say, a pure functional style manner versus common Lisp's approach and many functional programming languages that were invented at that time, an impure functional language. Okay. The obvious exception to that rule for those looking at computer history mainly is a scheme. But even in schemes cases, they ended up having what's called controlled mutability still with, I think it's called set bang, to actually be able to modify a particular cons value. FSET provides sets, lists, and so forth, and we're going to only cover kind of the transducers based libraries that are already there for you to use the transducer API. And then we can talk about obviously other stuff that's related to uh, the transducers API. But the main example that I want to kind of cover is something dealing with fset, and this is the simple example that's actually straight from our documentation. Let me just copy this one piece of code here that I want to cover. It was not that. Oh, fast immutable collections right here. Okay. So the first thing to start out with is actually we need to actually load, it looks like, the fset library. Okay. So if you look at ql system apropos, come on, and do transducers slash fset. Okay. We can see if this works. Let's see if this actually is already loaded as part of the core transducers API. Doesn't look like it, but we'll see what happens. Let me see if I do. Hold on. Let me just do this and do transducers. cl-transducers, JSON. Maybe I have to do fset here. Interesting. Let's see what I need to load. This looks like this API may not be already in. Well, let's see if this works with let's see if we have one. Transducers. Hold on, let me do it up here because I need my scratch buffer. Print transducers. Transduce. Okay, let's do transducers map 1 plus. And what we're going to do is we're going to map this to transducers. Oops, we don't need to put it. Hold on, we can do this. Transducers. Set doesn't exist. So let's see if fset set shows up. No, it doesn't. Okay, so it looks like I'm going to have to get a newer version of the transducers library and load it into my Lisp image. Not a big deal. It looks like this is a newer version than the version that came out. Hold on, let me go look at the release here. I thought that this went into this last night. All right. Not a huge deal. Let me do this. Okay. So in order for me to do this, I have to first go to eShell, do a quick git clone in my local directory. Okay, git clone. We need to grab the latest version of this, so we need to use this. Hopefully this will work. Um, oh shoot. Hold on one second. Let me try the HTTP version for the time being, because I know I have access to HTTP. Um, uh, okay, so let me exit out of this because we don't need this anymore. Go down, and we need to restart my Lisp because, unfortunately, I grabbed the quick Lisp loaded version, and I need to load the newer version. So hopefully transducers will load. Good. Now we're compiling the one that I have. All right. It'll take a minute just because since this is all since it's first loading the Lisp code, it's going to compile these to facils. So you get fast loading from then on, and then it will show up. Mm-mm. Okay. Hopefully now. And let me just check one thing here. And transducers. Um, okay, so I have to also now load here ql quick load transducers slash fset. Okay. Okay, so now we're loading fset now. Give it a second. Okay, and now we could do what we were going to do originally, which I think I could just simply pass in any collection here and we'll convert it into the appropriate fset thing. So this is now available to you at your leisure. It takes in any Lisp collection and it will convert it into an appropriate immutable collection using the transformation APIs. And the advantage of this kind of approach, I think, at least for me, when I started looking into this, is the fact that now you can take any data source that may or may not be necessarily in the transducers framework for doing transformations, okay? And with a little, not even any, as you can see here, it wasn't too much code at all to actually go in and be able to convert this collection into another collection. Obviously, this is a contrived example because it's only a list of 3 elements, but naturally, I could see you can extend this to multiple types of uh, examples. All right. There is one other library that I thought would be useful for folks to look into, but in order for me to do this, we were going to have to play around with it a little bit, and that is with transducers. There is a built-in JSON transformation library for those of you, especially who are doing stuff with web development programming, whether it be server-side scripting and or front-end dev, where you may end up having to write some of this code and would like in many cases to transpile it so that way you get efficient JavaScript code that would naturally work on the web. The JSON library is at your disposal and it's part of transducers slash JSON. as the name appropriately indicates. Obviously, I'm not going to cover everything here, but I wanted to come up with a decent example for this. And I think the example that I saw on the web, it might be a useful one to actually go and try, which is, yeah, we can do this one.
Hey,
So let's
Ram, I have a
start with just a very basic example, which is one that reads into a stream and writes to a stream. So you could think of this as essentially your standard, like, cat or. And the way we would do that is pretty simple. Okay, we obviously need to, for our sake, we need to start writing with output to string. Output to string. We'll take a stream. Okay, and what we're going to do is we're going to use transducers, transduce. Okay, and there's this thing called the pass function, which if you go and look at the documentation on pass here, and oh wait, before I do anything of this sort, I have to also load in the library because this is a separate library. It's part of the larger transducers package, obviously, but the ASD doesn't get loaded when you do the top level transducers library. And it's spelled like this. So if we do that and we load it, we end up getting our features for JSON, and we got our JSON parser. Okay, so now if we do, I believe it's just pass, right? Yeah, it's just pass. Okay, so if we go look at the transducers pass function, let's see what happens. So you can see that all it does is it simply is like an identity function, right? It's just passing along each value to the transduction. Okay. Um, it it's pretty useful for some of these kinds of things, obviously, because what we want to do is we want to actually, in this case, not necessarily um, do any sort of transformation. We're just using the map part to actually pass through and then provide us the stuff for the reduction. So we use transducers.pass for that pass through. Then what we do is for JSON, what we do is we grab the value. Actually, we do this. We do transducers slash JSON colon write. We can write to the stream. And what we're going to do is we're going to read from in our source, okay, some sort of JSON object. All right. Now this can also be, there are readers out there too as well in this API um, to read in from like a file or something like that. But for sake of example, we're going to just go ahead and read this from a string. All right. And this string is going to hold essentially an array which contains, sorry, which contains two JSON objects. Okay. One with name, let's say Bob. Obviously, we need to escape those guys. And then name. Oops. Undo that. I hate when that happens. Name Alice. And what this does is it'll just read in this as a normal JSON array, pass each value into the pass function, just like everything else, and then it'll then pass it to the write function. That's all this is going to do, and write this out to a stream. So when we run this, hold on, did I mess something up? Curly bracket when reading an array. Ooh, do I have to? May have to escape the curly bracket stuff. Um, oh, sorry. I forgot that I need to add a comma. Okay. Okay. It compiled no warnings, but the reason it didn't print it out is because we didn't actually tell it to print it out. Okay. And we could see that this would actually give us what we expect. It will actually go through and return Alice and Bob. Okay. Um, Now you may be wondering why uh, it didn't format necessarily Alice and Bob, the strings to be quoted. Um, that's actually something that I don't know. That is because of the write function of the transducers JSON API is treating those as escape coded strings for the time being. So it didn't actually do like an encoding of the quotation. So I'm not entirely sure how to make that pretty print so that it would be nicer for our REPL. But since this is actually giving you the proper arrays, I didn't think too much of it when I tried out this example. So those are very brief libraries for transducers. But what about series? And I saw somebody mention, I have to go um, look at my notes, that series with cl-transducers is possible. It's just that you have to do some some stuff related to it. Hold on. What is it? Um, all right. So I misread that. Um, Transducers doesn't have a series per se mapping to today. The folks that were talking about the series mapping were actually talking about how the package set of transducers map exactly to how series does transducers, but the data structures are slightly different. And I thought that it would be great to illustrate the differences between the two uh, the two libraries to kind of compare and contrast. So let's take, for example, let's see here. Guess would be mm, yeah, I guess we could do this one. All right. Let's take this first example, taking the first 1,000 and then incremented by 1 and getting the sum. If you recall this one, what this is doing is it is grabbing all um, the the list of ints starting at 0, okay, incrementing all the values, grabbing all the odds, and then taking the first 1,000. Okay. So what we would have to do in series is something similar, but the eager evaluation and how it's actually being written is going to be slightly different. All right. I'm going to put this as a side-by-side comparison so for folks can actually see it. So first we're going to have to load up series. All right. Load that up. Okay. So now if we wanted to get the integers, we have to do series scan int, I think it was. Hold on. Series scan. Where was it? It would be. There should already been like a. I mean, I could write this, but this is. I didn't think that I needed to when I did this last time. Scan function. Hold on 1 second. Documentation. Got to remind myself since it's been a while since I've actually done this. Enumerate the series type, specify the value returned by unit and step, and it returns as follows. Okay, so let's see. I could do integer. Okay, and unit is 0. Our step function is going to be, let's see, lambda x. Oops. Lambda x 1 plus x. Okay, so now we have, if I'm not recalling, we can do 0 is not of type symbol. 1 second. Oh, I have to give an init function. Sorry. 2. This is an init function. Lambda takes nothing and returns 0. And then it increments. So this works. So if we do this one, for example, here, when we run it, you can see that we get the infinite literatures. So now what we need to do is we need to filter these guys based on we need to, so we already now are getting essentially two out of the three. So instead of map 1 on infinite integers, we're getting infinite integers immediately through the step function. Okay, but we still need to take filter, and we still need to do take. All right, and then we need to then run the reduction, which is a collecting function. All right. So the first things we need to do is filter. Oops, sorry, that's my I have a, as part of Spacemax, I wrote a bunch of utilities to be able to quickly put wrappers around um, Lisp expressions using smart parens. So if I periodically accidentally type some of those, it's because I didn't realize I was in insert mode while I was typing. All right. Filter is not filter is a transducer, and in order for me to do series, it's choose. I have to use choose. Choose if odd. Done. So now if we run this guy and we print this guy up, you'll end up seeing that we get only the odd numbers now. But now we need to obviously run the third thing, which is grabbing the first 1,000, right? And that's our collection function. So what we do is we do again, and we do series collect. Collect length, I guess is what I need to do. Maybe. Hold on. Let's see. Oh, that's the length of the collection. That's not what I want. We want to do collect. Do they have any? Let me see what's collect. Okay, hold on. I'm gonna check collect nth, and then we can do collect function if that doesn't work. Okay. So what we need to do is probably do this one, which is the generic one. I didn't want to necessarily do this one just because it didn't seem that I needed to. Computes the cumulative value by applying functions to the elements and the things. The problem here is it's not taking it's taking an infinite collection, and we would have to keep track of the size of it. I thought that there was a way to like do. Oh, right. Got it. I think what I have to do is create a second scanner with scan range. Okay. Bam. This will work. So we do scan range to get the take again, which is another one, from 0 up to 1,000. Okay, this should work. Wait. What did I forget here? Up to 1,000, or let's say, actually, I could just say length 1,000. Okay, I have to provide. Wait, did I mess that up here? Hold on. Oh, okay. I designed this slightly different. I took the infinite integers correctly. Okay. Um, we don't want to do scan range because scan range is actually a faster way of handling the same idea. Because scan range is basically like a loop. Okay, hold on. I've already gotten the infinite integers. I should be able to retrieve. Um, choose choose collective. Wait, what is chunk again? Oh, sorry. Quit. Documentation series chunk. Right, but we want to do. Hold on. Let's see what's in here. Okay, so we have alter, choose, collect, chunk, collect file, collect length. Maybe I need to just do this. No, collect sum is actually going to not give me what I want. Scan file, scan inclusive, scan function, scan range. So I'm curious about this one. Maybe I need to do this. I need to do. Oh, wait. Let me try this one thing. What is collect do? Nope, that's not it. If I could do collect function with some generic thing, that would be ideal. But unfortunately, in order for me to do that, I would have to do a dirty, dirty, dirty hack, which is writing a closure around this and keeping track of the count myself. Which might end up actually making things a little bit more function to make this exactly the same. Because in series, if you wanted to do the same thing, you could have just simply done. What I'm trying to do is map it exactly to what the transducers has, but I know that you could just simply do collect sum of series. I think it's, if I remember correctly. You know what? I'll just do this on the REPL instead of, and then I can always paste it on later. So you do series, collect sum, and collect sum basically literally the reduction function on a series. And what you need to do is provide a series, and then you could just use scan range. Okay, and what you could do is do what's it? from 1 by 2 length 1,000, and this will give you all the odd numbers. All right, the first 1,000 odd numbers, just to give you kind of an indication of what this looks like before we actually call collect sum on it. It looks something like this. And then what you could do is obviously, since we have that, you could just do now series collect sum, and you get the same sort of idea. And the time at which it actually is doing is slightly faster, but the version that I'm trying to create is exactly kind of mapping what we saw here in composition, which is why it's taking slightly longer, mainly because getting the infinite series is not a problem. It's grabbing the next 1,000 element, the first 1,000 elements is something that I've forgotten. I have to go and look into. Uh, Folks,
Hey, Rom.
yeah, what's up?
So you want the first 1,000 transformed odd numbers, right?
I want the first 1,000. So I already have the infinite stream of infinite series of odd numbers here, right? This is what this
Right.
is here.
I'm just thinking that if you already know the length, right? So you want 1,000 in your new list or set or whatever, right? And in this case, I mean, this is a simple case, but why not just take the first 2,000, right, and then get rid of all the odd ones, right, and now you're left with 1,000 even ones, and then add one to each one of them. Then you have 1,000 odd ones.
But that's what the scan range is doing already for you, right? That's what this guy is doing, right? It's computing the first 1,000 odd ones. This is the same as what you're suggesting.
I'm just saying, I don't know. It looks like
It
why
looks
go
like
to
it may not be possible, just mainly because of the fact that infinite series in and I forgot about this to some extent. Infinite series in series. I hate to no for folks getting confused there. Series is library's name created a data type called series. All right,
the
that's a mathematical term for creating a computation based on some sort of summation there. And um, what we've created here is an infinite series, but for infinite series to be computed efficiently, and that is to eliminate any sort of loop possibilities, you have to have this notion of being online, right? So you need to be able to describe the computation in such a way that if a static analyzer looked at it, it knows how to compute those at compile time, and be able to write efficient code to eliminate any sort of loops or runtime checks that are involved. In this case, part of the problem is already given to us here in this piece here, but we need to actually keep track of and create a count of the number of these. So one way of doing this is, I know this is for folks who are going to look at this is going to be like, oh, this is disgusting, but if you want it completely identical to what the transducers library does, you could do something like this. Basically, you wrap this in a let form, okay, and we keep a count, okay, and say it's 0. Okay, and then we create another scan function here on top of scan. Okay, and um, the type is going to be integer. Okay, and the initial step that you're going to do is lambda and what's it?
Is
Um,
that let over lambda? Oh no.
yeah, it's lat over lambda. And we do uh, what is it? We would have to grab um, we'd have to scan the first lot, the first one. Um, let's see if we can do this. Okay, then we do 1 plus count, and then we return x. 1 plus count, return x, and we're doing the same thing for our step function. Um, and all we're going to do is we do uh, what's it? Uh, when I guess I should really write this as a second thing. And this basically is essentially using the count. Okay, when count is uh, when ah so when
Sorry.
no problem, when plus count 1. You might be wondering what I'm doing here. I'm just basically making sure that we count up to 1,000 here. Um, equal to 1,000. Then unless, sorry, because we want to unless we want to do this. We don't want to do when. Unless it's 1,000, keep doing the following, which is increment the counter and return the value. Okay. I don't know if this is going to work exactly, but it should. Um, we might lose a value or two here depending upon how I wrote this, but it should work. The one thing that I'm doubtful about is the init function taking in an argument. I don't think the init function can take in arguments because it's supposed to be an identity function. Let's see. Invalid number of arguments 0. Okay, so it is complaining about. Hold on. Let me see here. Okay. Um, so there's a scan. Ah, I got it. I can just ignore this altogether and don't return anything.
Yeah, exactly.
Yeah.
Right. So I mean, you have an infinite series.
Yeah, this should work. Okay. Let's see
But you
what
know you only want 1,000 things back. You know
oops.
that means you need 2,000 things in, right? So just go through the list and throw away ones that aren't going to work, right?
Yeah.
Instead of doing any computation on them, just like every other one, you don't even have to do any computation. Just go like A B A B, and then now you end up with a list out of your infinite, or a series out of your infinite series that's only 1,000 elements long, right?
Right.
And they're all our selector was give me the even ones, right? And then just run some RNA down the list and say, or the series, and say like, okay, add one, and the
I mean,
result
this is
is
basically what. So the infinite series piece already is taking care of all this stuff, right? What we're doing is we're essentially writing in Haskell terms take, all right?
okay. I don't
We're
care.
implementing basically take. And I thought take was available in or something of the notion of take is available in series, but maybe I was just wrong on that. Um,
Well, I mean, this is a very simple, small example, right? This isn't like running a whole huge supply chain or something like that. But in this case, we know we only want 1,000 things back,
that's right.
right? So we know that we're going to have 2,000 inputs, right? Because, if we add one to everything,
That's right.
then the odd ones will become even and we don't want them. So just go through and throw all of the ones that are, I guess, even, no, odd out of the box, right? And now we're only left with evens. But then we're gonna run a machine down the series and add one to everything and collect.
Right. I mean, you're you're effectively getting the same answer, but you're changing the
Yeah.
order of computation.
Well, I just,
No, no,
it's
and that makes sense. I'm not saying that that's wrong. I'm just saying
better not.
the I'm
Yeah.
just saying that to match exactly what we had here, we had to do some finagling.
Okay.
And that's just and honestly, it's not using series the way it was intended, right? So there e, e, transducers, this kind of shows the design of series is slightly different than the design of transducers, and it goes back to this notion of, and we've covered this when we were covering series, of online computation versus offline computation. Okay, so for
Okay.
folks who haven't seen my coverage of series or gone through the series library, to explain this a little bit, online computation, when we're talking about series, is what happens is when series is a compiler. Okay, first and foremost, the series Common Lisp library is a compiler for what could be perceived as a domain-specific language for functional programming. All right, and it uses this, and this is again, as I understand it, a model of computation that's essentially a source to sink model. Okay, so you have some sort of data source that you're going to quote unquote scan on. You're going to run through a series of transformations, which they call transducers, and then you're going to collect the results, which is what they call collectors. Okay, obviously, there's some additional extensions like gatherers and generators that were part of a separate extension that was in the library that we've covered. But this is essentially what series is from the get-go. Okay. For this transducers piece, which Clojure essentially adopted, and they did composable transformations based on the same set of data structures instead of reinventing the set of data structures like series did, they ended up going a slightly different route to do the same sort of eager computation that series does. Okay, series requires the computation to be um, what they call online. That is, if you run essentially a static analyzer, like if you treat this as a program that you're going to compile, you're going to run a static analyzer to go and figure out in the control flow graph if it is possible to certainly optimize a branch, all right, and especially in the cases for loops, which series is most often than not used to actually eliminate a bunch of loops. If it's able to address the loops in a much more efficient ways, it will identify that branch in the computation and compile it so that it's efficient. Okay. That requires at least though some notion of a stopping condition so that series can run the analyzer, right? In the case of infinite series, as we see with say things like scan range and so forth, you have to write some filters to actually go and uh, actually that might be another way of writing this. Now that I think about it, um, what's it? What was I going to say? You have to write some sort of filters to actually go and tell series, hey, this is a stopping condition. Go eliminate the computation here. All right. So in this other case here, this case that we're doing, this 1,000 case, another way of potentially writing this is, um, let me see, is probably through using choose. Um, Documentation on the generic choose function, series choose function. Sorry, I may have to restart my list because there might be a hanging computation that's causing a slowdown. I've been running this Lisp image for almost 2 weeks now, so I periodically, since I tend to do a lot of garbage computations in my Lisp REPL when I do exploratory programming, I have to periodically restore it so I can clean it up because there's no stop the world collection call in a running Lisp image, as far as I know. Uh, which is a good thing for folks who are listening, thinking that why shouldn't there be one? No, I think it's actually a good thing that they're not doing it, but you know.
I think it'd be cool to have like people that have long running Lisp or REPLs, right? Uh, dump all the definitions that were made by humans, right? And then print them on a T-shirt and sell them,
That'd be
right?
excellent. That's a great idea. That's a fantastic idea, Mr. Taylor. I expect the proposal and initial prototype on my desk tomorrow.
All right. I'm here to help. I'm a giver, you know that. I just
Yes,
give and
yes.
give.
Oh shoot. Okay. Looks like I'm gonna have to abort this guy. Where's Sly interrupt? Control C. Control C. You kidding me? Ugh. Restart Lisp. Kill my Lisp. I want you to kill my Lisp. There you go. Excellent. All right. Am I back in business? I am back in business. Okay. So what I need to do is first load transducers and then load series. Okay. And what I'm going to do is for series, I'm going to do series. Oh, I want to first do documentation, documentation, series, choose, function. Chooses the elements of items corresponding to non-element of bools. If items is not given, then non-element of bools. Okay, so it doesn't. It's slightly different. It requires essentially a mask. All right. Then what we do is we do okay. We do this. We do series. Actually, we do let count 0. We do then we do um, series choose if, sorry, if, there we go. And what we do is we do lambda x declare ignore x, because this is taking in a value, but we're not going to actually use it. And all we're going to do is say if um, uh, count is less than 1,000, return true, otherwise return nil. Okay, done. I know there might be other ways of handling this for folks who are watching this, but I think this will definitely work. All right. So now we have our lambda. Okay. But what are we going to choose on? Well, we're going to choose on series choose if odd p series scan. Oh, wait. I forgot one more thing here. And I will add that here in a second. Here, before we return nil, we do prog n. We increment the count because we're collecting the next. Okay, and then we return nil. Done. Now we do integer. It's a dirty integer. The lambda 0. And then we write our step function, which is lambda x 1 plus x. Okay. Let's see how crazy this is. That's it. There it is. So now we have our...
Yay.
Huh? Yes, yay.
I
Thank
said
you.
yay.
Okay. So now I could just do this and this hot. I'm not saying that you try this at home, folks. I'm not saying that you try this at home. All right. I'm saying that, it's, yet another way to do a compare and contrast. Okay. The series collect sum, collect, come on, sum. Okay. And here we do also WR print the actual sum, and let's indent these correctly because I don't like it not being indented correctly, and we run it. And if we go here, we shift it. What? Deleting unreachable code. What are you talking about, you crazy bastard? Non-terminating Lisp expression. What are you talking about? Hold on. We may not have gotten out of the woods yet. Deleting unreachable code. So this guy is not doing... Okay, hold on. Before we do this, we have to do one more thing, which is, let's see, R. series collect length. Okay, I just, I just, you see, it's running an infinite computation, which is why it's slowing down. If I run infinite series, I know now that when uh, I'm running something that's in the background that's killing memory because it's consing all the time. Series doesn't normally cons. It's just that when it's doing an infinite series, it does cons quite a bit, which is why very quickly you'll notice performance slow down in your Lisp image. You're like, why is this thing slowing down? It's because of the fact that it's kicking in the garbage collector all the time. So we don't want to do that. So my conclusion here is still slightly off. I will have to debug this a little bit more details because this is not doing what I expected to. It should have worked, but why it didn't work, I have no idea. I know the scan range stuff works. In both cases, if you saw the scan range versus the other one, you could see that like if we go in, let me just go ahead and restart this because I'm gonna wrap this up and then I will post this as another debugging session in a bit. But I wanted to first do a compare and contrast with the other version that I wrote earlier, which is this guy, not this guy. Hold on. That. Okay. Here, compare this with, say, what we had earlier, which was not class. You don't need to look at the print statement. The actual computation is collect sum of series scan range from from 1 by 2 length 1000. Okay. Okay. So if you look at the transducers version versus the version that we have here, that the quick one that I wrote earlier before we went on our little excursion on creating an exact replica of the transducers computation. Okay, and I'm just gonna go put the print so that folks can actually look at the differences between these things. Hold on. Print. Okay. Okay. Actually, I don't need to do that. Do this guy out here. Take this guy out because we don't need this either. CPW. No, no, no. CP. There we go. You can see that the collect sum and scan range version is slightly shorter. Okay, number one. Number two, you can also see that it's a little bit more declarative. It looks very closely to look like a list comprehension. The scan range version versus the transducers version. Okay. Consing wise, I don't believe there's much of a difference. Now we could check this out by doing a time, okay, in your Lisp REPL. You can actually do something like this. Grab the computation, print it out here, then come here. Let's see if I can get some adjustments. EWR, and let's time it. Okay, and when we run the computation, you could see the number of bytes that are getting consed here is about 2K. All right. If we run the version with series, you will see probably a slight improvement. you can see a slight improvement from the one in transducers. Now, that isn't to say the transducers library can't be improved from a performance standpoint, but it does tell you that it creates currently, the current version of the transducer library creates a significant amount of garbage compared to the series library, which is a bit more matured. In fact, you could clearly see in terms of just consing, the series did some optimization to make the entire computation cons free versus the computation that's in transducers. So that's all I have for today. Um, are there questions?
No questions. Thanks a lot. Very interesting.
Thank you. Let me see if there's any questions on. Okay. All right. Thank you for all joining me. Next week, hopefully. No, next week we'll be off. Unfortunately, something came up, so I'll be unable to do the stream next week. Um, and but we will be back for Labor Day. So I will see you in 2 weeks. See you later.